Hello, everyone. I'm Ankita. I'm a senior software engineer at Pinterest. I'm part of the storage and caching team, and I have been in the same team for 3 years. Today, I will be talking our journey on how we modernized our HBase workloads with TiDB. This is the agenda for today. First, we will go through the introduction, then motivation for adoption of TiDB, how we built our in-house TiDB platform, how our data migration journey looked like, what are some of the big wins at the end of migrating a 4 terabyte use case, and in the end, we will have Q&A. So what is Pinterest? Pinterest is a visual discovery engine for finding ideas like recipes, home, and style inspiration, and much more. The mission of our company is to bring everyone the inspiration to create a life they love. We are a planet-scale app with 1.2 million QPS, 430 million active users, and we manage 9 billion boards and 441 billion pins. The storage and caching team at Pinterest manages a lot of online, low latency, high QPS services like Zen, Exia, Sparrow, UMS, all backed up by HBase. Zen is the graph service, Exia is the index store, Sparrow is our transactional database, and UMS is the key value store. All these services form the backbone of Pinterest business critical use cases like ad, shopping, etc. We have one of the largest HBase footprint in the industry with 9,000 virtual machines in 50 production clusters, storing 6 petabytes of data on disk and serving 100 plus business critical use cases. So what is the motivation for next generation storage backend? HBase, although HBase has helped us in past several years to scale so much, it natively lacks a lot of features. So to get around it, we built Lego pieces, for example, secondary indexes, transactions, and a lot more. So this has made the architecture extremely complicated. At the same time, managing it has a high infra cost. So this motivated us to search for a new SQL database which can serve our customer needs for the next 3 to 5 years. These are some of the concrete examples of missing functionality and how it causes high system complexity. HBase lacks secondary indexes. So to work around it, we built a service with 5 additional components. It has high maintenance and high operational load. Similarly, HBase lacks composite indexes, which leads to inefficient data retrieval in our graph service. HBase also lacks cross-table transactions, which has caused data and index inconsistencies in Zen, our graph service. We do have offline jobs which run daily to fix them, but it has been a major pain point for our customers. So why maintaining HBase clusters has high infra cost? For each data set, we have 6 replicas. This is because we maintain primary and secondary, primary standby cluster pairs for high availability. Since HBase has a single shard serving architecture, for each, the HDFS layer has 3 replicas, but at the region server layer, there is only 1 replica. So this leads to high infra cost. So this is our vision for the next generation storage platform for next 3 to 5 years. Currently, we have Zen, Exia, Sparrow, all of these thrift services backed by HBase. We want to move to a structured data store, the next generation, a multi-API, multi-data model, multi-backend storage platform backed up by new SQL data store. So why are we doing this? This is because a lot of modules in all of these services are common. For example, authorization, rate limiting, hotkey detector, etc. So these can be abstracted away into a single service, because maintaining 3 services is obviously a lot harder than maintaining 1 service. At the same time, when we use these services, we are tightly coupling clients with physical resources and also with the data model. But with this kind of architecture, we are giving clients the ability to change data model, as well as they are not coupled tightly to the data store they are using. So in a few years, if we have to migrate away from the data store which we chose today, it will be much more easier than how it looks today. So this has been our journey so far. We started this project in H2 of 2020 by evaluating 15 plus storage backends. Our evaluation criteria was a comprehensive list of clients' feature requirements, consistency guarantees, scalability, operational support, community support, etc. After that, we shortlisted 3 backends, YugaByteDB, CockroachDB, and TiDB, for in-depth performance benchmarking and shadow traffic. Shadow traffic basically means we are basically mimicking the production traffic in a non-production environment. So we are testing at scale. After H2 of 2020, TiDB stood out in terms of stability and latency, so we decided to go with TiDB. In H1 of 2021, we continued our shadow traffic testing for each of our earlier data services, which I talked about, Exia, Sparrow, Zen, etc. We performed TiDB reliability testing for our platform. We worked on TiDB productionization in the Pinterest storage stack and worked on backup and restore for disaster recovery. In H2 of 2021, we designed the data migration strategy for all these migration of HBase tables to TiDB. We got our first use case onboarded. We integrated TiDB with Hadoop platform at Pinterest, integrated TiDB with a Pinterest in-house monitoring stack, and started working on the SDS design, which is the next generation multi-API storage platform. In H1 of 2022, we performed a lot of reliability improvements in our in-house TiDB platform. 3 more use cases were onboarded to production. We had backup and restore productionization, SDS productionization, and started working on TiDB offline framework. The TiDB offline framework will be used for migrating analytics workloads which are currently running on HBase ecosystem to TiDB ecosystem. So now let's learn more about how did we build the TiDB platform from scratch. We didn't use TiUp, which is the one-stop deployment tool provided by PingCAP for deploying TiDB, because there were a lot of overlapping features like deployment service, certificate management, monitoring stack, automation tooling, etc., for which the amount of work it had taken to integrate, to work around these was much more than So we didn't use TiUp because Pinterest has dedicated services for each of these features like deployment service, certificate management, monitoring stack, etc. So it was extremely hard to integrate, to use a TiUp at Pinterest stack. So we basically maintain the source code in our version control system as a monorepo. There are more than 5 components in TiDB's ecosystem, including PD, TiKV, SQL, dashboard, TiDB monitoring, TiSpark, etc. As of now, we have done more than 3 version upgrades. The last upgrade from 5.4 to 6.1 only took 1 engineering day. Since we maintain our own source code, we have the ability to have some local patches. For example, our own deployment scripts, which can be stored in our Git repo, although we try to merge any changes in upstream. This is a snapshot of how the CI/CD of TiDB looks at Pinterest. All of these components are built in parallel. using Jenkins job. This is a single TiDB Docker image, which has all of these binaries built in. It takes around 40 minutes to build it, and once it's deployed on an AWS machine, it can run as a Docker container. So for example, if you want to run a PD binary, you will run it as a you will run it as a Docker container using this image. TiDB cluster management. Each TiDB component is a unique environment in our deployment service. Now we have the ability to scale SQL and TiKV with a click of a button. All of the TiDB clusters are TLS enabled, and they are accessible to clients using an Envoy port, which makes it AAA enabled. AAA means authentication, authorization, and auditing. This is again a snapshot of how it looks internally at Pinterest. So for example, shared vanilla prod is a production cluster. These are the PD nodes. They correspond to this TiKV nodes for shared vanilla prod. So so shared vanilla prod PD will connect to the TiKV of shared vanilla prod. Similarly, we have for SQL. Building our in-house TiDB platform has been a great learning journey with some ups and downs. When we ran into PD split brain problem, what it basically means is PD is a HCD quorum having 3 nodes. Now, if a instance dies ungracefully, then it won't be deregistered from the HCD quorum. But if our deployment service brings up another node, it won't be able to join this quorum because it already has 3 nodes. So it would start as its own 1-node quorum. This was a very hard problem to diagnose because some TiKV is connected to the new 1-node PD, and there were no errors anywhere. Once it was diagnosed, the mitigation was quite easy. We just needed one check to ensure that the actual instances, the PD instances, are same as the ones which are registered in HCD. We also added host isolation logic for replica placement, which basically means that each replica will be stored in a separate AZ and on a separate host. We added leadership transfer logic to our deployment scripts for PD and TiKV so that there is no latency spike in case the PD leader transfers to another node. It takes only 4 hours or even less to create an empty TiDB cluster in our in-house platform. We have the ability to perform instance upgrades and version upgrades with no downtime. Now let's change gears and see how we built our data migration framework. We used Lightning, which is a tool provided by PingCAP. Lightning has 2 modes. The local backend mode, which has high speed and high resource utilization, but its downside is that the table is offline when the data ingestion is happening, so you cannot serve online traffic. On the other hand, there is TiDB backend mode, which is slow. Its resource utilization is slow, but it can serve live traffic during the ingestion. What were the goals of our data migration framework? We wanted a framework which can be used for online migration of all of our use cases served by Exia, Zen, Sparrow, etc. We wanted a validation strategy to ensure that there is no data loss and there is acceptable percentage of temporary inconsistencies. We also wanted to make sure that these inconsistencies can be fixed before the end of the exercise so that there is no client-side impact. We wanted no downtime, and it should be transparent to the clients. It can be repeatable, and we should be able to test it, and also it should be able to support strong consistency use cases. So this is the initial state for each of our services. This is how it looks. There is a client who talks to a thrift service. This thrift service can be Exia or Zen or Sparrow, and that connects to the HBase source table. During migration phase, we use the HBase source table. It's still serving traffic to the client, so the client doesn't know. HBase source table, we snapshot it, convert it to the CSV dump, and use the dump to ingest in the TiDB table using Lightning. So we used local backend mode for 4 terabyte use case because of the scale. But if the table is small in gigabytes or megabytes range, we can use the online mode. In step 2, now the TiDB table is ready, but it still has missed the live writes, which happened after we took the snapshot, because we never stopped the traffic to HBase, right? So there is a delta now. At this time, we created a double write framework on the service layer so that once the TiDB table is ready, whenever there are client writes, they get written to HBase as well as TiDB. But at this stage, the writes are async. This means we have not brought TiDB in a critical path. So if TiDB goes down, nothing happens. Client is still getting served from HBase. In step 3, we now took snapshot of HBase and TiDB and using a MapReduce job to compare the rows and stored the unmatched keys in S3 again. This is how we reconciled it. So in step 4, there is another MapReduce job which reads those unmatched keys, reads its latest value from the service. And the service is still being served by HBase. So basically, we are reading the latest value from HBase and write it to TiDB. After this stage, TiDB and HBase are exactly in sync. So we start double sync write. Sync write basically means if it fails in HBase or TiDB, the client is going to receive an error. So both of these databases should be highly available. In step 6, now we are ready to move away from HBase. So we are doing async write to HBase and sync write to TiDB. Basically, we flipped it. And the final state is client is being served from TiDB. These are some of the migration trade-offs. There are 2 inconsistency scenarios. First is if there is a storage backend availability, right here. So here we are doing sync write, and if the write fails in either one of them, we are returning an error to the client, but we are not rolling back. So this can cause inconsistency in TiDB and HBase. And the second scenario is due to race condition between double writes and reconciliation. So this can happen in this step. Basically, you are reading the latest value from HBase and writing the value to TiDB. Between these 2 steps, it's possible that a live write for the same row came and got written to TiDB, and you are overwriting it with a stale write in this step. So for both of these inconsistency scenarios, basically, whenever we reconcile the delta, they get fixed. In practice, when doing it for the 4 terabyte data set, we saw that it only needed 2 rounds of reconciliation to reach 5 nines of data consistency between both the tables of HBase and TiDB. These are some of the learnings from the data migration of 4 terabyte table. First is TLS certificate management. So as I said briefly before that, Pinterest has its own certificate management. It's called Normandy. It refreshes the certificates across the AWS fleet every 12 hours. During the migration, if the certificate gets refreshed, Lightning couldn't detect it, and it would fail. So it took a few rounds of failed ingestions to realize that the root cause is TLS certificate. This is because the logs didn't say anything about TLS, but it would just say region not found. So we collaborated with PingCAP and involved the subject matter experts, so thanks a lot for fixing it. Second learning is offline mode and online mode. So as I said, the online mode is less resource intensive but very slow. And offline mode is more resource intensive but very fast. We use the offline mode in a cluster which was serving live traffic. So this affected the actual live clients which were being served because it was the same cluster. We decided to create a new cluster for using offline mode. And later, PingCAP has provided us with placement rules, which is basically a workaround for this problem. Ixia double writes reliability improvements. So if we go back here, these double writes in sync and async fashion, it took a few iterations to get the availability and reliability which we expected here. So it was a learning experience as well. Support for Java key store merged upstream with TiDB Java client and MR connector. So all the infrastructure at Pinterest is TLS enabled. And when we were writing the MapReduce jobs, we realized that the open source TiDB Java client and MR connector, which is again an open source project in Ti Big Data repo, both of them did not support Java key store. We have merged the new feature, and it's in upstream. MR connector scalability issues resolved in collaboration with PingCAP. So while doing the reconciliation, doing the reconciliation here, when we were snapshotting the TiDB table, MR connector didn't scale for 4 terabyte because it was probably not used at this scale. So PingCAP helped us solving those issues as well. This is some background on the use case which we migrated as the first one. It's called admin history store. It basically tells what actions are taken against what user and their content and why. It's used for biannual transparency report, which Pinterest publishes on the website. So why do we need strong consistency for it? That's because the numbers need to be correct. And we were first serving this use case from Ixia, which only provides eventual consistency. So that's why we decided to move this to TiDB, because it needs strong consistency. These are some of the big wins after the migration. We saw 3x to 5x P99 query reduction with 14 indexes. This use case is 4 terabyte. It has 20K read QPS and 400 write QPS. Now we have strong consistency. The architecture is very simple. There is Ixia, which is the thrift layer, and then it's served by TiDB. Ixia's original stack has 5 more components because HBase doesn't support secondary indexes. So we basically used our in-house indexing store to support it, which made the architecture very complex. We have made contributions to open source community for the MapReduce MR connector project, as well as TiKV Java client. Also, we have some patches for Lightning. We were able to achieve 5 nines of data consistency between HBase and TiDB for the use case. We migrated it in 9 hours, and it had 14 indexes. And the reconciliation job took 8 hours after, obviously, a few iterations. So at this time, if we are supposed to migrate the 4 terabyte table again, it will only take around two days. And it has been running on TiDB for more than 2 months, and no manual operations are needed for cluster management. This is a big win compared to HBase, because in HBase, we have a lot of Puppet scripts, for example, for compaction, splitting, etc., which TiDB does by itself. So it simplifies the operations. This is the future work. Our end goal is to deprecate HBase from Pinterest storage stack. We will continue our reliability improvements on the in-house platform we built at Pinterest. We will continue migrating the use cases for Exia, Zen, Sparrow, etc. We want to put TiDB offline framework in production, which will be used for analytics workloads, which are currently supported by the HBase ecosystem. We want to start working on the TiDB CDC framework using TiCDC. So this is a journey which took us to more than 2.5 years, and there are a lot of people involved. So I would like to thank our management, Bo, Dave, David, and Liang Kong, our engineers, Alberto, Anish, Bin, James, Kevin, Lichi, Mark, Purajit, and Vivian, our interns, Antonio, Andreas, and Sangeeta, our PingCAP team, Adamo, Colby, Leo, Sean, and all the SMEs which get involved whenever needed. Our internal Pinterest team, Telatran, which is the deployment platform, security, Hadoop, Spark, Artifactory, and SRE, and all of our customer teams for supporting us with immense patience as we are doing this migration. Thank you. Any questions?
Hi, thank you for the talk. Question about your double writes in the service layer. So I'm curious about why you chose to go with this path versus a path like we did where you have consumption of HBase bin logs and then you sync it over to TiDB. Like, why do double writes in the service layer? And did you consider the alternatives?
So we did the double writes because we wanted to know the online latency of TiDB. So with the double writes, it's easier to know how TiDB performs right off the bat.
I see, makes sense. So you got early performance data by doing that.
Yeah.
Very cool, thank you.
So for the double writes, I would expect latency impact because it's real time. How did you deal with that? So
the double writes were async earlier, and then later it was in sync mode. Since TiDB's performance is at par or even better than HBase, that's why it didn't impact the clients. Yeah.
Yeah, so you mentioned it may take up to 4 hours to create an empty and a TiDB cluster. I was wondering what's the bottleneck? Is the virtual machine provisioning or is TiDB set up? Because the number sounds to me a little bit higher on a higher end. Thanks.
Yeah, thanks for the question. So it's a combination of all of them. Additionally, the combination is basically the provisioning time. On top of that, we are deploying the Docker container. And at the same time, you cannot provision PD, TiKV, and SQL concurrently. You first provision only one PD node, wait for it to come up, then you add 2 more PDs, and make sure that they join the cluster. Then after that, you start the TiKVs and SQLs. Yeah. Yeah.
Oh, hi, yeah, great talk. One thing that stood out to me is how you mentioned that you only need 1 engineer day to do a version upgrade for TiDB. And I would say coming from MySQL, this is very impressive. We took maybe a year to do our MySQL upgrade from 5.6 to 8.0. So 1 day is really impressive. I was curious if you could talk a bit more about what kinds of testing and validation you do when you do this version upgrade. And if you support things like a rolling upgrade and a rolling downgrade in case things go wrong.
Yeah, thanks for the question. So yeah, it took 1 day. It included basically upgrading the source code with whatever version we wanted to, 6.1 in this case. After that, we have different clusters. First is the test cluster where you do it, which is a very small scale cluster. You just make sure that the binary is running and the cluster is healthy and accessible. After that, we have a shadow cluster, which is production scale, but it doesn't have production data. So if it breaks, client will not get impacted, but at the same time, we are able to do scale testing. So after the test, cluster passes, we do the same deployment in shadow cluster, and once we have done all the validation and make sure that there is no latency impact. Another important thing is in the shadow cluster, we are doing, mirroring the production traffic. So it's exactly like production in terms of traffic, scale, etc. But the good thing is we can break it. So we are okay with, we basically do it there, and then only we do it in production. Yeah. So by rolling upgrade, we for PD, SQL, TiKV, SQL, yeah, all three components we do only one node at a time. So yeah, it takes time to finish the upgrade. I have not tried the downgrade. Yeah.
Hello.
Yeah.
Can you share more numbers for your further migration? So like you mentioned that you've migrated so far one service with 20K QPS and like 4 terabyte. What is like estimated numbers for like when you migrate your Zen and Sparrow? Like what would be size and QPS?
So I don't personally work on Zen and Sparrow, so I don't know the numbers on top of my head, but I will talk to you offline.
So it's just like order, like it would double it, or it's like 10x?
It's about 10x.
Okay, and any plans to move like your key value? Because you also mentioned that on HBase you also have key value, right? Like any plans to move that workload as well or no?
So the key value use cases are being migrated to an in-house key value service built by Pinterest, the rock store.
Mm-hmm.
Yeah.
Thank you.
Yeah. Yeah.
Sorry, can you please go back to one of your presentations? The flowchart that you showed. Yeah, so I want to ask you, so when you said you reconcile the delta from S3 to your, at what stage does HBase and TiDB are in sync? Because in the previous step, you, this is for the first step, you took a copy from the HBase database source and synced up TiDB. So there will be some delta, right? At what stage does the delta completely get synced up? Zero down, I mean, near real time, or I mean, because from what I see that you take it from S3 and reconcile it back to TiDB in step 4, right?
Yeah.
But I think even at that stage there will be some difference, right? Delta.
No, because here we are already starting the live writes to TiDB. So at this stage, so whatever delta happened at this stage, it never increases, because that's the delta after which we start live writes. And here we take snapshot of HBase and TiDB, right? So it will be the same delta which we will reconcile. So there is a possibility of inconsistency in this state where you read the unmatched key from HBase and write it to TiDB. But at this stage, TiDB is also receiving the live writes. So there can be a race condition and there can be inconsistency. But in practice, for 400 QPS, we saw that the inconsistency didn't happen. But if the QPS is huge, it's possible that we have to do this reconciliation step multiple times to ensure that the delta gets decreased every single time. And we have the ability to measure if the rows match exactly in HBase and TiDB. So unless they reach the threshold of 5 nines of consistency, we never start reads from TiDB.
No, okay.
Yeah.
Okay. Thank you.
You said you have not taken a downtime, which means you're accepting some inconsistencies in the data. Is that correct?
So,
because
yeah.
otherwise you will never catch up, right? You have to, there is always a possibility of some inconsistencies still remaining, no matter how many times you run it, as long as the online writes are also happening at the same time.
So the online writes are already reaching TiDB because of the double write framework on the service layer.
Sure.
Yeah.
But you can be out of sync when you apply them, right? When you're applying your delta, like you said in step 4.
So here we are applying the delta writes to TiDB, and at the same time it's also getting the live writes. So it's possible that we are applying the stale writes, as you said, right? That's the
Right,
question.
right.
But if you do it multiple times, the probability of those get decreased.
But never goes to 0. That's what I'm trying to
So for
understand.
400 write QPS, it went to 0 only after one round. Like the second round, when I did it, the numbers were 99.999 for the comparison between HBase and TiDB. But you might be right, like if the QPS is huge, then it might take several rounds and still it might not go to 0.
Okay, thank you.
Yeah.
Hi, I have a quick question.
Yeah.
Very good talk. It sounds like you're using the self-managed version of TiDB. Any thoughts in the future roadmap to go to the managed service cloud for TiDB?
By managed service, you mean basically using PingCAP to manage TiDB and build
Correct.
applications for it? I don't think that's a plan, at least for the next few years.
Okay.
Yeah.
All right. Thank you.
There's a comment here.
Yeah, so on the previous question, well, it's not a, but anyway, so the point is that we are capturing the deltas. The only key is that, because on a migration, the only thing that is important is whatever it changes. So in that sense, the process is relatively optimal in the sense we not have to, go through all the keys on the database, just over those that are modified. And the point regarding the previous comment that never goes to 100%, equality, that's true, but, doing a data migration with live traffic and getting 100% of, parity is yet to be seen. So yeah. Yeah, but you said, yeah, but you got downtime, right? We are not taking downtime. That's the key difference here.
Thank you for that. Any other questions? All right. Thank you very much.
All right, everybody.